Us. Okay. Here are the announcements. And I think I can't tell which of these is more important. The one I heard in the hall, and like I said, I had seen the title of the email, but just hadn't had a chance to open it yet. But I can't remember now for this class. It seems like most of you have paid, if not all of you, okay? But they are, I don't know if you've been here a while before, sometimes they let it drag forever. This fall, they probably are starting this. If you haven't paid by next Wednesday, as what I heard in the hall, you will be dropped from the roll, okay? So please try to get the payment complete by Wednesday. If you can't get it all complete, at least talk with someone in the business office, explain what the situation is, and they may be able to put some sort of marker or thing on your thing to keep you from getting removed from the roll. What's that?
I was thinking about it earlier, and I thought I did. I hadn't done mine yet, but then I remembered I did.
Okay, well, that's good. Yeah. Well, what you can do, I don't know where you look to find out, but I can look on the class roll. If you have an asterisk by your name, I know you haven't completed payment, and if you have, then, but I don't know where you can see that, because you can't see the class rolls.
Possibly from your student suite.
I would think it would be somewhere there. I just don't know where to tell you to go for it.
I think it would be like when you're under student information, I think it may be under there.
Okay.
With,
See, I don't see any of that, so I don't know. Huh? Yeah.
And also, if you go to an advisor or something, they can check their little green letter.
Right. Yeah. Yeah, I can check and find out, but I can't tell you how to check and find out. Okay. And by the way, registrar's office, the cashier's window, any of those people can tell you that as well. But please, if you know of anyone who's not completed payment, tell them to get that wrapped up by Wednesday, or get in touch with the cashier's window, the business office, somebody, let them know what your situation is, so I guess you can put a flag on it to keep you from getting dropped next Wednesday. So please get that done. Okay, but here is the good news type side of things. And that is, I did finally get to talk with Mr. Weigel at the planetarium last evening, okay? And he says they're really booked right now for the month of September, except for two possibilities. And these are general shows, wouldn't be just for this class. So the only two things available in September are general shows, and one of them is this evening at 5. And the other one is the last Thursday in September at 5. So then once October gets here, that first Tuesday at 2 o'clock, he could fit us in then and just have our class. So if y'all wanted,
That sounds great.
which one?
The October one?
The October? Are y'all okay with that? Okay. It'll be a long time since we did the astronomy part, but that way it'll be our class. Okay. So we'll plan to do that. Yes.
I think it'd be very beneficial to us if it was just our class in there.
Yeah.
So I agree with that.
Yeah. Well, the shows are good too. You just don't get the chance to ask questions and interact as well. I mean, he always allows for questions and stuff like that, but with a big class. The last time in the summer, the only time available was the general show, and that was it was summertime, it was middle of the day-ish, and there were lots of kids running around making a lot of noise, okay? And so he sort of geared it more for kids. The 5 o'clock probably won't be as many kids, but this way he can pick something that he thinks would be interesting to you, okay? So we will plan on it. So we'll meet here. This is way in advance, but just to get it out there so everybody can hear. We'll meet in the class on that first Tuesday. I think it's the second or third, whatever it is, fifth or whatever it is. The first Tuesday in October. We'll meet here in the classroom and then head straight over there, because if we meet here at 1:15, it takes sometimes as much as 45 minutes to get there. Usually not, but it is pretty close to it because it's at Stanford University. Yeah.
Traffic isn't that bad in that way. I have to travel it sometimes every 2 or 3 days in the week. So it isn't that bad, but it's you just gotta watch out for people swerving there.
Yeah. And one of the things is they are doing construction in malfunction junctions, and if you go through that, you never know what's going to be the slowdown there. Okay. So we'll meet here in the classroom and head right down to the car. So if you typically can't, I'm preaching to the choir here because y'all are here, but if you typically are late getting here, then you might need to just plan to drive straight there. Okay.
Because you just plan to drive straight there anyway?
Yeah, you can. That's perfectly fine. You don't have to be here. But I was just saying, in case people need to carpool or something like that, we'll meet here in the classroom and then head out. I can carry comfortably 3 and possibly more in my vehicle if someone wants to ride with me, because I'll be coming back here to campus afterwards. Okay. Now, what we'll do, we'll leave here at 1:15. Get there at 2, and he usually runs a show somewhere between 1 and 2 hours. So say 3 to 4, sometime we'll finish. Then we'll come back here, and there will be time to wrap up and do some things here. So you don't have to come back if you don't want to, but what is? Huh? Yeah. The field trips, that sort of creates that.
But if you go to bus.
Okay. Now, if you want me to get the vehicle. I can see if I can rent a vehicle, but the largest vehicle that the school has is a 15 passenger, but they don't let you hold 15. I don't remember what the number is, 12 or something like that. So not everyone can fit in one van. So some of you still need to have your own transportation if you can. But the last time we talked, I got the impression that all of you don't want to get down on your own.
So you saying the last 2 hours, get there too?
Yeah, get there at 2, and I don't know if he'll do a full 2 hours. You think he usually does it like an hour, hour and a half, something like that. Something between 1 and 2 hours. So if we got there at 2, he'd be finished at 4. By the time we got here, it'd still be 4:45 at the latest, very latest. We go until 5:45, so we have another hour plus of class. So I'll come back, even if it's just recording things on Screencast-O-Matic, we'll do that. And by that time, who knows what will be in the oven. And that's getting pretty close to the time that we'll have our field trip to the Channel 13 station if we can get there. Because that's next to the last chapter we do. So we'll be getting pretty close to that. So we may have 2 field trips really close to each other. So we'll see. Okay, so we'll figure on that, and I'll just let him know we're coming on whatever that first Tuesday is. Yes?
When is our research paper due?
Anytime you can get it in. The last possible day to get it in without losing points is the last class day, not final day, last class day. And that's, I can't remember, maybe the
very
second
last day
Tuesday.
of class in October is the 12th.
Yeah.
So that means we will meet that Thursday. The 13th. We meet supposedly on the 12th of October.
Okay.
That last Thursday, which is when, do you do final exam last day?
Well, that's the thing. I believe first mini term is over that week, second mini term starts the next week. So we have final exam the last Thursday, the last class day will be the last Tuesday.
So October 12th would be the last.
Yeah.
That's the final.
And how long does it need to be? Like
What?
the paper?
1 to 2 pages. 1 to 2 pages. Double space, standard font size. 1 to 2 pages. And remember, a page of text. That means if you have lots of header or something else, and then you get down and start typing right here, your title, your triple space. Start typing here, 1 page of text goes to the bottom of that page, and on the second sheet of paper comes down at least that far. That's a page of text. So it'll be at least 2 pieces of paper, but 1 page of text. At least. Shoot for 1 to 2. It can be longer. I don't take points off for that unless you're late coming in. No, I'm sorry.
Do you read them all?
Of course I do. You don't think I would have you do this and not read them, do you? I actually.
I've always heard things about
First Tuesday of October.
and he actually cares about reading through everything and giving your grade to what you deserve.
Okay. All right. Now the news was 2 things. I don't remember anything about who's paid and who hasn't. If you know of anyone who hasn't completed payment for fall term, supposedly next Wednesday is when unpaid students will be removed from the roll. Now, if you know of someone who hasn't completed payment but they're in process and something's pending or something else is going on, please let the business office know. They can put a flag out there and keep you from getting removed, I think. I don't know. I haven't seen the email itself. I saw the title, but I didn't get a chance to read it, but someone told me that's what it was saying. All right. And the other really good news is the class decided that unfortunately it's a ways away, the first Tuesday in October, I can't remember what date that was, 2nd, 3rd, 5th, something like that. First Tuesday in October is when we can go to Planetarium Center. And and we'll have the show to ourselves. The place still. So, and we'll talk later about whether we want me to get a van to help with the transportation, or if everybody's wanting to carpool it and just go your own. So we'll talk about that. We've got plenty of time.
I think carpool is good, but if you're going to be driving back at 4 o'clock in this traffic, you really think you'll make it back? More classes?
I've done it before. Yeah.
I believe you.
Yeah. 4 o'clock isn't bad yet. After 4 may get bad, but 4 o'clock isn't too bad. Yeah.
We all went as a group in the van last night. It's quite an experience.
It would be nice, but I don't have a van. I don't have access to a van that will hold 20 people. There's 20 people in the class. I'm 21, so I can get the biggest van we can, and it technically is a 15-passenger van, but they say the insurance only covers up to, I think it's 12, and that may include the driver. So that means we all can't, unless we can get 2 vehicles, but then I have to have somebody else driving that is authorized to drive. So it does get to be sort of a logistic problem. I've wondered at times if we could use the school bus. There is a bus that carries like teams to the games and things like that. I think there's a pretty hefty charge for that. There's no charge for the vans or the cars and things like that, but I think there's a charge for that. But I can try to find that out. And I agree, it would be sort of fun to all go together, but with this big a class, it's hard to find the vehicle big enough. All right. So that's on for them. Now, by the way, and since you just came in, along about that time, we're probably going to be scheduling our second field trip, the one for the weather chapter. So that's going to be right around that same time. So that week we may have 2 field trips, one on Tuesday, one on Thursday, or really close.
Which one? Which channel?
13. Yeah, on Red Mountain, right by Vulcan Park. Okay. Any other questions? All right. Okay, let's talk a little bit about today. Today we're in Chapter 18, Plate Tectonics. We got a good start on it last time, a reasonably good start, and I do believe we'll have a chance to finish the chapter today. Now, I already used a fair amount of time, but if we finish it before 3:15, then we'll have time to do the lab. And I took the labs down to have copied, slid them under her door last night, because she, wherever they were. Yeah, slid them under the door last night, but she wasn't in this morning when I came in, so They're not in my box, so I don't know if I hope she's in by now and has got them copied. But if not, we'll have time. I can get them copied.
You didn't print the test. Then what?
Yes, and then the last 30 minutes is the test. I was getting to that. That's why we would start the lab at 3:15, so you would be through by 5:15, so you could start the class at 5:15 to be through by 5:45. However, today's lab is a really short lab as far as what we're doing in the lab. Today's lab has some, not like your moon lab, but somewhat similar. There are a bunch of questions. There's only 10 points worth of stuff in the lab today, so the remaining 15 points you get from answering questions at the end of the chapter. So that can be done at home. So if you want to, when we do the in-lab part and you're through with that, you can continue working on the questions if you want to, so you can get it all done and knocked out today, or you can take the test and take the questions home and do that. So you have a lot of options today. Okay. So I think we'll have time for the lab and the test today. The test, of course, is on the previous chapter, chapter 17. The lab is sort of on chapter 18. From now on, the labs just kind of, they cover multiple chapters, kind of. They cover stuff from multiple. Like plate tectonics, we can't move around any continents, so there's not much we can do in that. So there's something else we will be doing that's relevant to it. And we'll be doing that for the next several labs. All these kind of tie together. All right, any other questions? All right, let's then hit where we left off last time, which is right around page 465 in the new text. I can't remember if I mentioned seismic tomography. Fairly interesting title there. A CAT scan, I don't know if y'all are familiar with that, that's computer-assisted tomography. That's what the T stands for in CAT scan. Well, that's a diagnostic imaging procedure that uses, some type of radiation, X-rays or magnetic resonance or something else, or actually computed axial tomography, okay? And basically, and I don't know what kind I had, but I had one of the heart, and literally they took the pictures, and then the computer chopped the heart up this way, and this way, and this way, and you could look at every view of the heart virtually without ever impacting the heart. I mean, all they did was inject the dye in. I was on the treadmill, and that kind of stuff. Got the blood pumping, had me rest for a certain time, and then they ran me through the machine, and then they did the pictures. So the computer axial tomography. Well, there's something similar to that in seismic tomography, and this little blurb talks about it. It's a pretty interesting application, so it's well worth a read there. Okay, now, I think we hit the other figures, so let's move on to evidence from Earth's magnetic field. What kind of evidence are we talking about? Evidence for plate tectonics, and here's Chelsea. Okay, now, and by the way, time out, let me say this again. 2 bits of news. One is, and this should come out in your email. Check your Lawson State email to find this out, because it should be there. From what I understand, they're moving up this term. If students haven't paid by next Wednesday, they will be removed from the roll. So if you know of anyone who has not completed payment, please let them know they will be removed from the roll next Tuesday. However, if there's some really complicated or important or some sort of mitigating circumstances, please go by the business office or cashier's window or something. Explain to them what's going on. They may be able to put a hold on to keep you from getting removed from the class if you know of anyone that's in that way. Okay, number 2, and this for this class, the field trip, and the other students decided on this before you came in, that the field trip we'll take to the planetarium will be the first Tuesday in October. Okay? And I can't remember what date that is. 3rd. Is it the 3rd? Okay, the 3rd of October. and those who need to meet here in the classroom at 1:15, because we're leaving right at 1:15, and then we'll head to Sanford and should be able to get there by 2, and we'll start at 2. Okay, if you can't be here by 1:15, then just plan to go straight to Sanford. Okay, does everybody know how to get to Sanford? How about where to go when you get to Sanford? Okay, we'll talk about that as we get closer to it. Okay, I have a map. I can make some copies of that. Okay, and what we'll do, if before then, we'll talk about whether I need to reserve a van. So I think up to 12 or 11 students maybe can ride in the van, but then the rest of you have to find, share rides and that kind of stuff.
How long is it going to be down there?
What's that?
How long is it going to be down there?
Okay, usually it goes at least an hour, and it's somewhere between 1 and 2 hours.
So, do we just go straight home?
What's that?
Do we go home when we be done?
I'm coming back to campus, and we'll have continue class or whatever we're doing at that time up until 5:45. I mean, I've got to bring the van, I've got to come back anyway, and so we'll just continue. Okay, I didn't know it would be that bad of news. Sure. Okay. All right, so let's get back to this. These are evidence of plate tectonics. So evidence from the Earth's magnetic field. Okay? That the plates indeed are shifting. This is some of the strongest evidence. It's a little complex how it is, but when you think about it, it really makes sense. Igneous rock. What kind is igneous rock? And here's Fred. Goodness, we may not get very far today because we're coming one at a time. Okay. A couple pieces of news. One is, and you should have an email about this, so check it. But I believe next Wednesday they remove all students who have not completed payment. So if you know anybody who has not completed payment for this term, be sure they get the ball rolling by Wednesday of next week. Okay. Okay. And, well, you got to Wednesday, so you check today, tomorrow, Monday, or Tuesday. Okay. We're going to the planetarium the first Tuesday in October, which is the 3rd of October. Yeah. Okay. We had a chance to go either today or the last Thursday in October, but the class decided the first Tuesday. Okay? So, if you need to, you can meet here at 1:15. We'll be leaving right at 1:15. If you want to drive straight there yourself, you can do that. Okay? I'll have a map for you and that kind of stuff ahead of time. And then when the show's over, which will be somewhere between 3 and 4, we'll be leaving to come back to campus. Okay? Now, I was also saying there is a chance. Here may be an opportunity in case we may not get back to campus. If the 2 field trips land on the same day, we'll be there first and then drive on to the weather station right after that. That is a possibility. I don't know if it'll be through with that chapter then. But the other field trip, if we can make it, schedule it, will be sometime right in that same time period. Okay. All right.
Thank you.
Now, let's get back here. The question are, what are igneous rocks?
Yeah.
Is it red?
The burn.
Second.
The fire, the burns.
Okay. It actually is a fire burning. It's molten rock, hot rock. Molten rock that is resolidified. Okay, that's what makes it the igneous rock. And if that's coming from deep in the earth, what's the big content of a lot of that rock from deep in the earth? What element? Iron. Exactly. That's why most of your volcanic rock is dark colored, because it has a lot of iron in it. Okay? So if that molten rock is making its way to the surface and then is resolidifying, okay? Iron is one of only 3 elements that is naturally magnetic. If you have your text, you can turn to the periodic table at the back of the text. You'll see these 3 are right in a row on the fourth row, just about the middle of the table, iron, cobalt, and nickel. Now, two of those three are found deep in the earth in good quantity. What are those? Iron and nickel, exactly. So two of the major components inside the earth are magnetic materials. Okay? So they make their way to the surface as a liquid. They solidify on the surface. Okay? And what happens to a magnetic material in the presence of a magnet? Like if you took it and stroked it along a magnet, what would happen? It becomes a magnet. It becomes magnetized. Okay? Now, if that iron, and maybe a little bit of nickel in there too, makes its way to the surface and cools fairly slowly so that and of course the Earth has a magnetic field, right? Mm-hmm. Okay? Has a magnetic field, then the iron molecules will tend to line up with the Earth's magnetic field. Let me point to the north. Now, if it goes real quickly, like glass, volcanic glass, it doesn't have time. Yeah.
All right. So when you said Earth was formed a while back, so do you think that by way of hitting Earth and broke off, that it magnetized this? I'm just trying to.
I see.
Theory.
I see where you're going. I see where you're going with it.
Did it magnetize itself or create a magnetic field to where it's always just our moon?
Okay. No, what holds the moon to us is gravity. That's the thing. The magnetic forces aren't that distant. Okay, but it's a good thought there. But here's one of the problems is, this is rather bizarre. I cannot explain why this happens at all. I'm not sure anyone can. It's probably a Nobel Prize waiting to be won. If anyone can figure out this one. I have my own little theory, but that 25 cents still won't buy you a cup of coffee. So I'll tell you what I think is happening there, but I don't know for sure. Okay, but when the Earth has a strong magnetic field, there's these field lines. Okay, now if this iron and nickel maybe too, is solidifying fairly slowly, then they tend to line up, the molecules tend to line up with, or the atoms with the Earth's magnetic field lines, which makes the rock magnetite as opposed to hematite. In other words, it's naturally occurring magnetic rock. Okay? Now, we know that happens. That's where magnetite comes from. Now, there are other times it just is hematite. It doesn't line up that way. Okay? Now, here is the strange thing. That's understood, sort of. Kind of. Okay. The igneous rock record of the Earth's magnetic field, strength, and direction. Here's the second part of this problem. The Earth's magnetic field is sometimes stronger and sometimes weaker. And then sometimes stronger and sometimes weaker. If that happened when the Earth's magnetic field was pretty weak, then you won't have that much magnetite forming. It'll all be hematite. If it's when the Earth's magnetic field is strong, then you have quite a bit of it. So, these volcanic activity, the stuff coming up and settling out, that goes in layers, and those layers record how strong the Earth's magnetic field was. Okay? Now, the magnetite poles, that's the iron ore that's magnetic, locked into an alignment with the Earth's field upon crystallization. That's what we were just talking about. The Earth's magnetic field varies in strength and direction over time, and here is the strange part. For they have measured now 22 times that magnetic field has reversed itself over the last 4.5 million years.
I'm sorry. Like,
yeah, that this is north, and maybe in a few thousand years, 100,000 years or so, that may be north. And then it reverses again. In 4.5 million years, there have been about 22 reversals of that magnetic field, as recorded by the iron layered in the thing. Now, here's my little theory, okay? Now, of course, we talked about before what makes a magnetic field? Moving charge. And it has to do with the spinning of the Earth and the liquid core and knocking off electrons. So it has charges floating around in there, that turbulent flow and that kind of stuff. And that moving charge is what creates the magnetic field. Now, I cannot figure out why this would happen, but this sort of makes sense physically a little bit to me. If that magnetic field is varying in strength, let's call this a very strong period, okay? And then it gets weak again. And it gets weak, it almost disappears. It may even go to zero. But then when it starts back, it's in the opposite direction. It's like a sine wave. You've got it. That's exactly what I was thinking. Weak, strong. Weak, strong, weak, strong, and therefore, and it happens very, very slowly. I don't know why. I don't know what would do that unless that turbulent flow inside, if it's along the axis, that's fine. But if it starts doing this and goes like this, then it's not going to be strong. And then it gets strong in the other direction. And lots of things follow periodic motion. I've just described periodic motion, sine waves. You nailed it when you said sine waves. If that's happening, that to me sort of explains reversals, strengthening, weakening, and reversals. Now, I don't know if that's the pattern, but I suspect it is. Okay?
What's the moon score?
What's what?
What's the moon score? Is it
What?
core?
Core. Oh, okay. I think they say it's kind of semi-liquid because it's not as big as the Earth, so therefore there's not as much heat from pressure. So whether it's strong enough to completely melt, it may be it's a liquid core, but a smaller liquid core. I don't know. I wouldn't be at all surprised if it doesn't have a very weak magnetic field, but I don't know that. I'm guessing. Could be a good paper topic. Okay, it could be. Okay. Now, why are we talking about the Earth's magnetic field in Plate Tectonics chapter? That's the puzzling part, except for this. Okay? Say again?
I'm sorry.
No. You may be right on it. Okay? So here's what's happened over time. You'll have a layer somewhere down here where and by the way, the Earth's magnetic field, if I say which way is north, what would you say?
That way.
Would you say that way?
Yeah.
Okay, where am I pointing here? I'm pointing out into space. Because guess what? We live on a globe. The Earth's magnetic pole is down that way because it's around the globe that way. The compass points this way, but if you let it float completely freely, it would float it would point that way. Well, that's where the North Pole is, somewhere down there. Okay, so that's why they show these arrows pointing down. Some of the time they were this way, and then later they were pointing that way, and then this way, and then that way. So that has happened about 22 reversals over the past 4.5 million years. Now, how do they know this? They have drilled cores down. Okay? And the cores will show hematite going this way, and then hematite going that way. So they have measured these. They have actually physically seen those cores. Willie is here. Okay, here we go again. Two pieces of news, and both of them are important, that's why I want to say them. One of these is, and I saw the email, and you probably have received the email too. Someone in the hall told me what it said. I didn't have a chance to read it yet. Next Wednesday is the last day to pay for a fall term, or else people are going to be removed from the class. So if you know of anyone who has not completed payment yet, tell them they need to get on the ball before next Wednesday. Okay? Now, if you know someone who can't meet that deadline, but know that it's in the works, please let the business office or the cashier's window have them go by there and explain what the situation is. They may be able to put a hold on to keep you from getting removed from the class. I know they did that one summer. They really screwed it up one summer. The next summer they did a little bit better. So that's one piece of news. That's a little bit of a downer news, maybe. But the other one's a very good news. I finally was able to talk with Mr. Weigel at Stanford University of Christmas area Planetarium. He said we could come the first Tuesday in October. I think it's the 3rd of October. And we will be doing it. If you want to meet here, we'll meet at 1:15 and leave at 1:15 to go to Stanford. Okay? If you can't be here at 1:15, plan to just head straight to Stanford. Okay? And the show will probably start right around 2-ish. Okay? And we'll talk about plant parking and where to go and that kind of stuff. All right. Now, back to this. So here we have these layers. How do they know? They've taken cores and they've detected these layers where the magnetic field reverses direction 22 times. Okay?
That's in the crust.
That's in the crust. Exactly. From volcanic material.
That's before you get the oils and the oil layers and stuff like that. It's just.
That's what?
How far down you figure that is? They drill?
How what?
How far down?
How far down you figure
Oh
they drill?
boy, I don't even know.
What they drill with? Diamond?
I don't know. I imagine so. I imagine that's the only thing that could cut it. Okay? But here's how that ties into this. Okay? And it's going to be a little bit before we come back to it. If plates are moving, there's 3 ways they move. I'm jumping a little bit ahead. Plates either move apart, they move together, or they slide past each other. We'll get to that later. And if plates are moving, someplace they're coming apart. Okay, someplace they are. And that creates these oceanic ridges because that's where the magma comes up from. When the plates move apart, it has a place for magma to come. Okay? These coincide with these, when it says submarine earthquake, that means beneath the surface of the sea earthquakes. There's a lot of those going on we don't even hear about because they're underneath the ocean. Okay? Seismographs can probably detect them.
So why do they use the word submarine?
Because what that means is sub means below, marine means ocean. So a submarine is a ship that goes beneath the ocean. So an earthquake, the submarine is one beneath the ocean. The Hawaiian Islands are all volcanic islands. Sometime in the past they were volcanoes beneath the surface. They kept erupting until they got big enough to be above the surface. Yeah.
So did you see that on the news when those people was at that crater and the little child fell in and they were trying to save the child and the mother and father fell in also?
No, I didn't. Where was that?
I didn't get where it was at, but it happened this week.
Wow. Was that
They said it was
a volcanic crater?
yeah.
Wow. I'm guessing out west somewhere they have the big volcanic craters.
They said they don't know whether it was quicksand or pulled it in
Yeah.
or what.
What's going on at Yellowstone Park right now? Because I saw a little glimpse of it.
Hopefully they ain't about to erupt.
They're saying something about it erupting, and they're trying to find a way from so much pressure building up at the bottom.
If that thing erupt, everything gonna go dog.
What's this?
In Yellowstone, like what he talking about, is possible eruption.
Yeah.
And they're trying to prevent
They're
it.
trying to prevent it. Yes. If they erupt, it's gonna go dog.
Okay. You mean it's going to be such a big major eruption?
Yes.
See, I hadn't heard that. All I heard about Yellowstone was that they were having a snowstorm this weekend.
Yeah.
I mean, a major winter storm this weekend.
Come on.
Yeah. But I didn't know that's in no way connected with what you're talking about. It sounds like what you're talking about is a seismic event.
Make you go down in a volcano.
I don't think it's a seismic event. It's just like pressure. They're saying pressure is building so much under Yellowstone Park that they're trying to find ways so it doesn't get that bad.
Really? Wow. I mean, the whole reason Yellowstone
would go about that, but
Yeah, we're playing with fire literally there. We don't know what, if we do this, what's going to happen then. If we drill down and saying that may create the hole that it all comes through, you know, I don't know what they're, I mean, it's a very interesting thing. Maybe a great paper topic if you can find enough on it. Okay, that'll be fine. Okay, So, here's what's happening. You have these submarine earthquakes where the earth is splitting apart underneath mostly the Atlantic Ocean, but it happens in other places too. And what you have is magma coming up, and it solidifies once it gets into cold waters there. Okay? And that makes a ridge right along that area. They call it a rift along that crest. The crest is where it comes up and it comes out. Large amount of heat escapes from that crest. It's sort of like a long linear crater, basically, is what it is. That's called the Mid-Atlantic Ridge. Okay? And that has been determined. They can go through with sonar and measure as you leave, say, Europe or North America, and head out. Of course, the depth in the ocean gets deeper and deeper, and somewhere about the middle, it gets less deep. There's a ridge there, right in the middle, pretty much, of the Atlantic Ocean. And it goes north to south. Now, it's not straight. It's a real curvy ridge. We'll see it in a minute. We also have oceanic trenches, where there's a real deep area. Let's see if we can get a picture of those. Okay, here's the ridge. And actually, Iceland is another volcanic island. It's a whole country. It's right on that. That's a place. Yeah, Iceland. Yeah. Okay. I think y'all are thinking some pretty good thoughts there, because Iceland probably, as far north as it is, as cold as it is, Iceland pays less for electricity or heating than what we do. And in fact, the whole cities are kept heated basically for free. No, volcanic. Yes. The volcanic rock is so hot, what they do is run water over it, and that water comes up warm, pipe that into people's homes under the floor, keeps them warm all winter. Constantly piping that water over the hot volcanic rock.
Free heat.
Huh? Free heat. You got it. It's called geothermal. Way to go. Really nice. So if you live in Iceland, basically your homes are heated for free. Almost. You probably pay a little bit of something for the maintenance of the piping and the pumping and that kind of stuff, but basically almost free. They don't use any electric heat. They don't need to do wood heat. Coal, no burning coal. Their electricity is geothermal, from letting that get down on hot rock, turning to steam, turning the turbines with that. I mean, it's great stuff. Okay, but that is part of that. That's the one place where that ridge has made its way all the way to the surface. Every place else here is just a ridge still underwater. Okay, so that's going on. The trenches are usually near the continents. Okay, because if the plates are moving apart here, which is what they are, that's why the ridge is there, volcanic material coming up, then somewhere they have to go under. And they do that near the coast. Not on the east coast of the U.S. I doubt if they do it on the west coast of Africa either, or Europe. I don't know that for sure, but we'll do this later in the chapter. In our course, you'll see this. But these are long, narrow trenches or deep troughs with steep sides, always run parallel to continental edges. I know this happens on our west coast. It happens on the west coast of South America. Here, I was on a ship in the Navy for 3 years that went out of the San Francisco area. And when you went out into the Pacific, if you were watching the depth, it just plummets. I mean, it goes straight down. In the Atlantic, it's very shallow, way out there. In fact, sometimes on the Atlantic beaches, you can go out almost out of sight and still walk on the sandbar somewhere out there. I mean, it's called the continental shelf on this side, but here it's the deep trench. And that's the oceanic trenches. Now, why are we talking about that anyway? It's important, but what has that got to do with plate tectonics? Well, it certainly has a lot to do with it. We'll see a little bit later. So here's the hypothesis, that the seafloor is spreading The hot molten rock moves up from the Earth's interior, emerges along the rift. The outflow is in both directions, and it creates new rock. Igneous rock came from magma, right? Both directions, new rocks. And here's what the drilling evidence has shown. There's thin sedimentary layers near the ridge, becoming thicker toward the continents. Well, that sort of makes sense. It's thin here because it's very new here. But then the closer to the continents, the older and older it is because more stuff is going on top of it. Okay? And it becomes thicker toward the continents. There's older fossils caught in that rock. No old fossils caught near the ridges. Okay? So the closer you get to the rifts, the younger all the material is. Okay? Now, this is an okay picture. Okay? These layers out here are, by the fossils they found in them and other things like this, 65 to 135 million years old.
Wait, they found fossils out there?
Yeah.
In the middle of the ocean?
Yeah. I mean, yeah.
Well, okay, so that goes back to the theory that
Yeah.
everything separate, like it was all laying there, so you
Yeah.
think.
Okay. If you have magma that comes up and spreads over the existing bed,
Right.
whatever shells and snails and clams and other things, they get fossilized right immediately.
So it would destroy them though.
It does kill them, but they remain sort of intact. Later they can go in and test that using what they call carbon dating.
Right.
It's a lot like Match.com. No, that's not. Okay. They use carbon-14 to measure how old it is,
Right.
and they can estimate pretty good from that. Not exact, but pretty good. And they found very old stuff in these areas. And this ridge here, on either side here, 53 to 65 million years. And this blue ridge here on either side, that's 38 to 53 million years. And the sort of sage green here, that's 23 to 38 million years. And this right near the ridge, that's only 5 to 23 million years. And the dark green in the middle, 0 to 5 million years. Now that sounds like it's really old, but guess what? Compared to this out here, that's almost new stuff. Okay? And they found this consistently. Okay? Near the ridge, it's all newer fossils and things like this, and the further out you get, much, much older. Okay? So we know that's been happening for a long, long time. Okay? Now, paleomagnetic. What does that mean? Studying the magnetic patterns for long, long periods of time. Paleomagnetic. Paleo means old. Old magnetic patterns of the magnetic strips on the ocean floor, basaltic rocks, those are the ones made from iron, the black rock, okay? You find identical magnetic patterns, reversal patterns on both sides of the ridge. Identical. Same approximate thickness and everything else going in the same direction. The patterns match those found elsewhere, providing age determination, how old that was. And guess what? Near the ridge, you have very few of those. The further out you get, you have more and more and more. Okay? Meaning that this is new material here, evidence of C4 spreading. Okay? Now, I don't find this illustration to be all that great. Okay? Yeah, there's a thing here, but what you ought to have is layers like this. The layers form like this. They show them as vertical layers, which doesn't make a lot of sense. Yeah, those spread out, but then you have the next, but they spread out into horizontal, semi-horizontal layers, and, you know, I see what they're saying here, but the plates are spreading here, and you have newer material, or you have this material, then that is older than this, and both of those are older than that, and it just keeps spreading. That would account for what they see in the age determination, and also the layers of reversals. You don't have as many reversals Okay. Kendrick? Okay. All right. Huh? Don't tell him. Yeah. There's two bits of pretty important announcements. I want to make sure everybody heard it, because if you're coming in, you may not go back and listen to the first part and you'll miss the announcement. One is, now I haven't seen the email itself. I saw the title of it, but I haven't had a chance to read it. But I just saw another instructor in the hall, and she said, for any students who have not completed payment for fall term, by next Wednesday they'll be removed from the rolls. Now, if you know of anyone that fits the boat, if they can't possibly do it, but there's a plan in place for them to get it done, then please let the business office, the cashier's window know, have them go to there and explain to them what's going on. Because otherwise you're going to be removed from the rolls. Okay? The second bit of good announcement, this is really good news. I finally was able to talk with the guy at the planetarium at Sanford, and they are booked solid through the month of September. But the first Tuesday in October, they do have a 2 o'clock available for us. So we're going the first Tuesday in October. Now, sort of interesting thing, that's going to be very close to the same time we are going to do our second field trip. We go under the weather station. So we may have 2 field trips right back to back. I guess it's conceivable we could do them both on the same day, but I doubt if that's going to happen. But we'll see. So anyway, those are the 2 bits of news. Okay. So this is more evidence that C4 is spreading. What they determined here. So I found it's a little disingenuous to have vertical slides that should show the layers going out horizontally or somewhat horizontal. Okay. Now, let's get back to plate tectonics itself. This was all evidence from the ocean that we've been talking about there.
And we still haven't reached the bottom of it yet.
What's that?
I said we still have not reached the bottom of it yet.
In many places we have. I mean, the Atlantic has been much more studied than the Pacific, because there's a lot more traffic across there, or at least our traffic has been. And there's a guy at the end of this chapter, I'm pretty sure his name is Herman Hess or something like that. He was a naval officer, and his main function in the Navy was doing research. He went out with these research vessels. They weren't fighting ships, they were research vessels, and they literally mapped the bottom of the ocean. They took core samples. They took a lot of these things that we've been. He's the one responsible for us getting a lot of these data. And there's been others as well. Okay? So let's put all this together, and this now is the subtopic, lithosphere, plates, and boundaries. Okay? This is the whole basis for plate tectonic theory. Now, of course, we don't know this without a doubt. This is our best guess. The lithosphere, tell me what the lithosphere is made up of. Okay? What portions of the earth?
Right under the ocean floor, I know that.
Okay? That would be the oceanic. As opposed to continental. Okay, everything above the asthenosphere. And what's above the asthenosphere? The upper part of the mantle and all of the crust. That's what I was looking for. The mantle and the upper part of the mantle, all of the crust, everything above the asthenosphere, that's what we call the lithosphere. But these are not, it's not one solid lithosphere, it's plates of lithosphere, broken into fairly rigid plates. Notice the term fairly rigid. There are weaknesses in those, okay? And they may have varied over time. The plates move ever so slowly on the asthenosphere. There is movement of those plates. Most, not all, but most of your earthquakes, your volcanoes, and other rapid changes in the Earth's crust occur most often at the plate edges, at those boundaries of those plates. And like I was saying before, there are three major plate motions. Divergent, meaning they're moving apart. Convergent, meaning they're moving together. And transform, meaning they're sliding past. But sliding is not the best word for it. Moving past. Okay? Here is that picture we saw earlier of these plates and a general indication on what direction they're moving. General, they don't have it good. Here's that mid-Atlantic rift, and that makes the boundary between, say, the North American plate and the Eurasian plate, between the North American plate and South American plate and the African plate. Okay? So this is a divergent boundary there between those plates. The Earth isn't growing any bigger, okay? So if it's diverging in one place, it has to be converging somewhere else. And that's what these show. These are largely converging plates, moving into each other, okay? And you'll see some of that. Others of these are transformed. They're moving past. These are general arrows. This plate's moving this way, that one's sort of moving that way, this one's moving this way. Here's converging plates, absolutely. The Nazca plate and the South American plate. The Nazca plate is subducting underneath the South American plate. Something's got to give, okay? And what happens there, when it goes under, it creates volcanic activity, it creates earthquakes and stuff, and that's why the Andes Mountains have grown right along the coast. You talk about a trench. Right there, you go out in the sea, and immediately the bottom of the ocean goes way, way down. Does that in our west coast too. The Atlantic, this is all part of the North American plate. Half of the North Atlantic Ocean is part of that plate. So the boundary's way over there. That's why we have a long, gradual continental shelf on the eastern side. We have a deep trough on the western side. Okay? We'll come back to this a little bit later too. But here's something else sort of interesting. The Indian plate is kind of moving up this way. It's Indian-Australian plate. Who knew Eurasian plate doesn't include India? That's a separate plate. India-Australia, they're on the same plate. Not on the same plate as these countries in between, but on the same plate here. Well, this is a converging plate, a continental plate and a continental plate conversion. Oh my goodness, what's going to happen there? Where are they going to go? Nowhere to go but up. Okay? When they go up, guess what you find here at the north part of this plate? Mountains. Guess what mountains? The Himalayan mountains, the tallest mountains in the world. And they're still growing because the plates are still colliding. Very, very slowly, but they're growing. That's why the Himalayas are so tall. Second? Okay. So we'll get to that a little bit later. But those are the three kinds, and those are the boundaries. Okay? Now, the answer to this question, it was also a Johnny Cash song, but it had nothing to do with the Johnny Cash song. What is this general area called?
The Ring of Fire.
The Ring of Fire. Okay.
The Ring of Fire.
Yeah, I thought he was starting to say that.
I like old Johnny Cash.
Yeah.
That's my man.
That's where most of the volcanic action and earthquake action goes on, is in the Pacific. Because if the Atlantic is spreading, then the Pacific has to have collisions in it. That's the Ring of Fire. Volcanoes, earthquakes. Okay?
Wedding ring.
Second?
I said the wedding ring.
Yeah. Nah, hey. My wife will beat you up. No. Okay. Let's look at the first of those divergent boundaries. Occur when the two plates are moving away from each other. When that happens, the molten material rises from to fill the fissures in between, rises from and through the mantle to fill those fissures. Okay? That forms new crust, like we were just talking about, and you see that in the evidence there, often accompanied with volcanic activity. And what was that island near the top of the northern part of the Mid-Atlantic Ridge? Yeah, there it is. You commented on it. Island country up there? It sounds like it's really cold. Iceland, you got it. Iceland continues to have volcanic activity on it. It was formed by volcanic activity. Volcanic activity underneath the ocean, all in here, there it reaches the surface. In fact, it wasn't too many years ago, I'm guessing 5 to 6, maybe 10 years ago, there was such a major volcanic eruption in Iceland. This map doesn't show it well. This, by the way, is Ireland and Great Britain right there. That there was such a major volcanic eruption there, the ash was spreading down toward Europe. They had to close many of the major airports in Ireland, certainly in Iceland, in Ireland, in Great Britain, in Paris, and some even in Spain. Why? The ash has some pretty mean stuff in it, and the airplanes don't like to suck in that stuff in the fragile jet engines. Yeah. That could cause some pretty major problems. So they actually grounded the flights until there was small enough amount of ash in the air so they felt like it was safe to fly again. And I mean close to a week in some of those busy airports shut down completely, okay, because of volcanic activity in Iceland. Okay, so much of the volcanic activity occurs, it can occur there. Okay, I was on the next slide. Okay, molten material rises, new crust, often accompanied with the example is, the classic example is the Mid-Atlantic Ridge. That's the one we saw here. That separates North America from the Eurasian plate here, North America from African plate there, and South America from African plate here. Okay? Major ridge, moving apart, divergent boundary. Okay? Yeah. Now, here's the picture of what their best idea is. The asthenosphere is down here pretty deep someplace, but here, because the plates are moving apart, it encroaches here and gets pretty close. So when you're asking how far down, it depends on where you are. If you're near a ridge, it may not be as far. The ridges are high, yet that may not be as far away. You have magma here making its way to the surface and then moving on both sides, forming new crust here. This, by the way, is the oceanic crust, made out of what material predominantly? Oceanic crust? The what? What kind of rock? It's molten rock, and what kind? It's igneous, absolutely. What kind of igneous rock? The salts. Fine grain, because they cool quickly. They're underneath the ocean. They got to cool really quickly. Fine grain, very dark, high iron content. That's what makes the oceanic crust. Remember, it's denser but thinner than the continental crust. Since we're there, what makes up the continental crust? Say again? What is the predominant rock there? Granite. Is acid igneous rock. Is it as dark as basalt? No, it's very light colored. Is it as dense as basalt? No, it's very low density because it's mostly silica, which is lighter weight than iron is. Okay? So you have the crust, and then this is the upper part of the mantle. And this makes the lithosphere. Here is the asthenosphere. Now, I don't think it's really all that thick. I think it's much thinner, but for illustrative purposes here. And that semi-liquid, you can actually have magma here, and that magma makes its way up and grows. Many editions ago, they sent us a packet of CDs, okay? And on one of those, for this chapter, they actually had a underwater camera taking pictures of that magma bubbling up into the bottom of the ocean floor and hardening really quickly. You can see that happening, but you can just see it spilling out. And they moved the camera along, and it just followed. It just was one of the most remarkable things I've ever seen. That actually the magma coming up, they were catching it on film. Really incredible. All right, that's divergent boundary. Convergent boundary means coming together.
Yeah.
Okay?
Towards each other.
Say again?
I said towards each other.
Okay.
Towards each other.
Yeah. Okay? Occurs when two plates move toward each other. That's exactly what you're saying. The old crust may be destroyed in the process because, okay? And here's when it does. Okay? When the old crust and when they move together, you got two possibilities. They go up like the Himalayan mountains, then the crust isn't destroyed, but more likely, one of them goes underneath the other one. This crust that goes down goes underneath the other crust and ultimately gets down where it's hot enough, it remelts. That's why it says it's destroyed. Old crust may be destroyed in that process. When it goes beneath, that's called a subduction zone. Again, sub means underneath. It's forced underneath the other part. That's the belt with one crust subducting under another crust. That's what happens where the west coast of the U.S., the Pacific plate goes underneath it, and that's why you get that trench there. Okay. Subducted materials partially melt, rejoins the mantle, and then later may come back up as magma again. So here we have three possibilities here too. You could have the converging continental plate and oceanic plate. Okay? You could have converging two oceanic plates converging. Okay? And you can have continental plates converging. Okay? Let's go back real quickly.
Now, all these plates are attached, right?
Okay.
They are all attached some kind of way, correct?
Not really. They're floating on the asthenosphere. Now they're not moving very quickly. They look like they're attached, but they really are free to move. Okay? The entire plate. Now remember, they used the word for it earlier. What was it? Mostly connected. There may be weak areas within a plate. Okay? Let's go back to the plate picture that we had here. Okay? This would be an example of ocean continental plate subduction. This is oceanic plate coming here, continental plate already in place. They're colliding, they're coming together. This is ocean continental plate conversion. Okay? Out here in the Pacific, you have Pacific plate here, Philippine plate here. Those are both oceanic plates. They're converging. Okay? Keep in mind, we're going to come back to this in just a few minutes. Okay? Something pretty significant is happening right there. And here we have continental plate converging. And by the way, and they don't show a real good picture of this, here is the African plate converging with the European plate. Okay? And I have a feeling, and this is my suspicion here, that zone actually goes up the Adriatic there. I think most of Italy here is where that conversion is happening. Because what's Italy fairly famous for? Oh, besides that. Okay. He's thinking pasta. I can hear him. Okay. Okay. Mount Vesuvius ring a bell?
Yeah.
Mount Etna ring a bell?
They use their
What's that?
They use their volcanoes because
Yeah.
they have the same surface as Mars. They send their rovers to test it there.
Oh yeah, okay. So I didn't know that. Okay. There's lots of volcanic activity there. And just north of there, northern Italy, southern Germany, Switzerland, what do we find there? The Alps. A mountain range. Again, this plate is being pushed under the other plate or pushed against it, and you have a mountain range growing there. Here, oceanic plate, continental plate, you have the Andes Mountains. Here we have the Sierra Nevadas, the goodness, what's the name of that small mountain range? Here, we'll hit it later. But you have mountains. You know what island country this is right here?
Philippines.
Japan. Okay. What's Japan famous for? Volcanic activity. Mount Fuji is a volcanic mountain. And also, okay. Sometimes it's good to be hard to hear. I don't hear as much of the peanuts. Okay, no. Okay. And remember, does the word Fukushima ring a bell too? What was that?
Hiroshima?
No, Fukushima.
Fukushima?
Say again?
Isn't that one of the mountains next to Kilimanjaro?
No. That's in Africa. Fukushima was the.
Oh.
Yeah, what?
It was like a major earthquake.
Major earthquake, because it's right there on that boundary.
Mm-hmm. And it did something to a nuclear power plant.
It did something pretty bad to a nuclear power plant.
Oh, that's the one that was on the news.
Yeah.
In
your lifetime.
Yeah, I remember that.
And then there was another little incident over there too, where they had big fireballs inside of the city, and pretty much part of that city is now deserted. Pretty much like Chernobyl.
Yeah. That's probably all connected with Fukushima.
And there's actually a town, I think, somewhere in Colorado that is abandoned, just like Chernobyl, because of seismic activity in the area, because it lit, for some reason, seismic activity lit fire to that coal rich town underground.
Wow.
It's been burning for about 50 years now.
Wow. And then in Pennsylvania, New York type area, somewhere up there, 3 Mile Island. I don't know if you remember that one. We just barely missed having a Chernobyl there in the U.S. I mean, our safety backup systems were much better than Russia's were, the Soviet Union's was, and we caught ours, but it still came really close to a major meltdown. I have a feeling no one lives on 3 Mile Island either. Now, I don't know that for a fact, but I bet you that's the case. It's in some river somewhere in either Pennsylvania. I don't think it's as far up in New York or somewhere. So yeah, there are some of those. But this is, Fukushima happened because it was two things: earthquake followed by a tidal wave. The tidal wave is what overran the nuclear power plant and caused all sorts of problems. Their power went out. They couldn't control the reactors anymore. They overheated, melted down.
Did they ever shut those reactors down? Did they ever get those shut down?
I think they did, yeah, ultimately. And in fact, that story is just really amazing. I don't know what you think of the general Oriental people, but the Japanese have a very strong community structure. And what happened there, I'm pretty sure of this, a bunch of older, retired men who had enough knowledge of what needed to be done there, they volunteered to go in and do that really hazardous work there, because whoever was going to get exposed to that was going to get radiation poisoning and die. And they said, look, we've lived most of our lives, don't send the young men in there. Tell us what to do, we'll go do it. And they did. And probably, I'm guessing most of them are dead by now, but they knew it was coming. They volunteered to do that. I'll tell you.
They're pretty much, their motto is, over there in Japan, Japanese, is pretty much put others before yourself.
Yeah. Unless you're the emperor. No, I'm just kidding. Okay. Yeah, except for that, yeah, okay. All right, so that is examples of oceanic continental plate convergence, oceanic plate convergence, continental plate convergence. I just wanted you to see those, see they really are there, okay? That was convergent boundaries. So here are the three possibilities. Converging continental oceanic plate, like the Nazca plate and South American plate. Converging oceanic plate, Pacific plate with the Philippine plate, for instance, and many others. And converging continental plates, in the India and Eurasian plate against the Eurasian plate. And there's pretty major events happening at all those converging. Yeah, okay. We got plenty of time. Say this again.
What's the line that runs through California?
Okay, the San Andreas Fault. We're going to get to that in a couple slides. Okay.
Yeah.
All right. I'm still ready. All right? Okay. Now we're going to look at each one of those three individually. So let's start with ocean-continental plate convergence. The oceanic plate, tell me something about oceanic plates. You've already told me a few things today. Oceanic plates, what's the primary material? Basalt. Oceanic plate basalt. Tell me two things about the basaltic. Two characteristics of it.
It's green.
Okay, fine grain. Second?
Light color.
No.
Dark color.
Dark color. Why dark color? And what content? Second?
Low.
Yeah, that's what it made of. What elements in that? Iron, heavy iron. So if it's got more iron content, it's also denser. It's denser. Okay? Continental plates, continental material, continental crust. What's the primary rock? Granite. Tell me two characteristics of granite. Light. Two ways it's light. Light colored, but also light density. So if you have a thin, and that was the other thing, oceanic plate is usually thinner, continental plate thicker. If you have a thin, dense plate, heavier, it's going to tend to go underneath the thicker, lighter plate, right? And sure enough, that's what happens. The oceanic plate of the denser basaltic material subducts, sub means underneath, subducts under the less dense granite type continental shelf. Okay? So that's what happens. Marked by oceanic trench, where that goes under, it drags down. Let's see if we can get a picture of that. Yeah, there it is. Here's the oceanic plate, the thin, dark, dense basaltic rock goes underneath the continental plate, which is mostly granite material, lighter weight, lighter density, lighter color too, and it subducts under that and goes underneath there, which makes a trench fairly close to the boundary. Okay, see some of this continental plate is under the water. This is totally under the water, and it drags some down, making a trench there. That's what you see in the Pacific. You left San Francisco Bay, the bottom just goes out, and then it comes back up a little bit as you go back out there. So now, yes. No, Florida is more along the Atlantic Ocean. You have these long continental shelves, so you don't have that drop off there. Okay? South America, big drop off there. Yeah, same type thing as here. Now, what happens underneath here? That basaltic oceanic crust has been forced to go down. It doesn't want to go down there. And guess what? These are not nice smooth boundaries like they show here. These are jagged, rough, rocky boulders sticking out of them. They get hung up on each other. Okay? And then all of a sudden, the pressure is there, though. The pressure is there, and then suddenly they'll give, and you know what forms then? And there's a sudden release of energy. Okay, that's partly volcanoes, but mostly earthquakes. Okay, now the volcanoes, yes. These are grinding past each other. The deeper you go, the hotter it gets because you're closer to the core, right? So it gets hotter anyway, but then the friction is huge when they're rubbing against each other, and that forms new molten material, and that's why you have deep-seated earthquakes here where things let go all of a sudden. You have heat produced by the friction and the fact that it's closer to there, and so you have magma making its way up where there might be a weakness or something there, and here all along the coast you have these coastal mountain volcanoes. Out west, okay, in the Pacific, the whole Japanese island chain, volcanic mountains, okay. Our western coast, there is Mount St. Helens, there's Mount Rainier in Washington, there's Mount Hood. All those are volcanic mountains fairly close to the ocean for this very reason. Now, not all of them are active. Now, one of those is Crater Lake. I hope that wasn't the one that the child fell in, but it could have been, because that's a beautiful, beautiful area. I've not seen it myself. I've seen pictures of my nephew when he was going to catch a ship in the Navy. He took a long trip out west to see a lot of those areas. He went by Crater Lake and really, really liked it. But all those are extinct, at least for now, volcanoes, because they were all part of this. So that's where those ridges come into play. They mentioned them earlier. Here we see them. Now we have ocean-ocean plate convergence. Okay, ocean-ocean, they're both basaltic layers. But something's got to give. One of them, for some reason, goes underneath the other one. Okay? That forms a trench that's already beneath the ocean. It forms an even deeper trench. Okay? And the underwater ridge could be created by that subduction, where it pushes the other one up. But you have a trench there, so the trench and ridge are right next to each other sometimes, associated with deep-seated volcanoes. We'll talk a little bit later, like 2 or 3 chapters from now, about the classes of volcanoes. These are deep-seated volcanoes. You also have the island arcs form, where you have the subduction of one plate going under another one, and all along there you get underwater volcanoes that ultimately reach the surface. Those form the island arcs. We're going to go back for just a second and look at that. Subductive material rises above sea level through the overriding plate. Let's see the picture first. So here's an oceanic plate here, another oceanic plate here. This one subducts under that one, making a trench here, but a ridge there. Okay? Why the ridge? Because this plate going under creates earthquake, volcanic activity, finds a weakness here, and you have these little volcanic mountains come up. And these will form an island arc. Okay? Real near a trench. Okay? Now, let's go back to this picture. All right? Somewhere right along here, I'm pretty sure it is. They don't show enough detail here to tell. There is a trench. It's called the Marianas Trench. It's the deepest part of the ocean anywhere on the globe. Okay? That's an ocean-ocean trench. I think the Pacific Ocean undercut the Filipino plate. The Pacific plate went under, but they're both oceanic plates. They have a very deep trench there, and the Marianas Islands are an arc island chain that form along there, one of those being Guam, I'm pretty sure. Okay? Guam, and laid further up here, the Filipino Islands, which are mostly volcanic islands. And like I mentioned before, and we'll get to this, there's the Japanese island chains, again an arc island. Does anyone know what this is? This is Alaska here. Here is an arc island chain, the Aleutian Islands there, okay? They form this thing. Why? Because you have oceanic plate convergence there. Actually, North American plate largely is continental, but there it happens to be oceanic too. So, and down here, there's New Zealand, right at the boundary. Volcanic island chain, right at the boundary of the Indo-Australian plate and the Pacific plate, these islands. Here is this whole area here. This is Malaysia, Indonesia. Indonesia is mostly islands, and they're all islands along plate boundaries, and they make these arcs. So they're just all over the place here. Okay? Those are the ones I know the best. Okay. Now, let's go back to our ocean convergence. We, I think, hit this one. That's what forms those island arcs. Japan being one very clear example of it. Okay, then you have the continental plate convergence. Okay, the less dense granite is bumping against less dense granite. Hey, no one's going to go underneath here because these are continental plates. So what do? They resist subduction. Nothing goes under, so they have to rise. Okay? Colliding plates pile up, literally rise, producing a deformed and thicker crust of these lighter weight materials, granite-type materials, and the Tibetan Plateau, Tibetan Plateau, and the Himalayan mountains. That was the example of the India, Australian plate, continental plate, bumping against the Eurasian plate. Tallest mountain range in the world. In fact, I'm making a guess here. I've read it somewhere. It seems like the 5 tallest mountain peaks in the world are in the Himalayas. There's Everest, and then there's another one, then there's another one, then there's another, and then somewhere else you have another, and then they come back and do. So they're some of the tallest mountains, and they're still growing, okay, because of that plate convergence. Very, very slowly, but they are growing, okay? So here's the deal. A continental lithosphere, granite, lightweight, light density, hit another continental lithosphere, granite, lightweight, light density. Nowhere for them to subduct, so they have to pile up, okay, forming a mountain range. While some of you are still writing, example 18.3, I usually don't stop and do the examples here, but if the distance between the Tal, which is on the easternmost point of Brazil, that's in South America, and Mount Cameroon on the western, central western part of Africa, if they're about 5,000 kilometers apart, which we'll use that as a rough thing, how long did it take them, if indeed that was plate tectonics, the diverging plates there, how long did it take the South Atlantic Ocean to open 5,000 kilometers if the average rate of spreading was 2.5 centimeters per year? Now, 2.5 centimeters is awfully close to an inch. 2.4 centimeters is 1 inch. So they're spreading at a rate of an inch a year to do 5,000 kilometers. Okay, that's just playing around with math, the answer is 200 million years. Okay? It's not happening quickly. You're not going to notice it, these plate movements. Okay? That was pretty interesting. They asked the same thing for eastern coast of Argentina to Cape Town, Africa, about 6,900 kilometers. How long did it take? And that was about 212 million years. Okay. Now, there's also, well, if some of you are still writing, on page 469, measuring plate movement. And this is partly how they do this. So if any of you were interested in, is this really happening? This is a description of how you do it. A lot of it is now being done from outer space. They can actually measure pretty good precision. Okay. They say that the military, I don't know if this is true. Okay, our GPS came out of the military needing to keep up with ships and planes and submarines and that kind of stuff. And later they said, okay, we can sell this, and people started selling it, and now we have GPS. But they say that the military, now this is what I've heard, this is probably classified, and no one will ever admit to it, but I've heard people claim that they can read basically almost like license plates from outer space. I mean, they have technology that is just about that good, your GPS only gets you within a few 10 meters or something like that. They can pinpoint things to less than a meter, I think. So pretty incredible. So they can do some pretty good close measurements from way up there. Okay, there's some more examples here. They're talking about slopes of the subducting plates. If you're interested in doing that, it's pretty simple math, but they tend to make it sound pretty complicated, but they can do that. So there's continental plate convergence. That's the last of the three types of converging plates. We've already talked about diverging plates, where they're moving apart, converging plates where they're coming together, three types of converging plates. What's the third type of plates movement? Transform. So let's move on to transform boundaries. That occurs when two plates, and the term slide is not the best one, when they move past each other. It's nowhere near as slick as sliding, okay? It is moving past each other. The crust is neither created nor destroyed. Crust is created when you have diverging plates, destroyed when you have converging plates, one's being subducted, okay? But neither created nor destroyed in transform boundaries. It's just moving. Now, the thing is, they're not smooth. They're jagged, they're rough, they're irregular. And if you have two plates trying to move past each other, and they're not slick as snot, they're just there. They're getting hung up on rocks, on boulders, on all sorts of things. And they try to move. The pressure is there to move, but it's hard to happen. Suddenly something will give. And that sudden jerk has nothing to do with anyone in class. Okay, no. The sudden jerk is what produces earthquakes. When you have that sudden release of energy, say some rock broke or faulted or something, there you have the earthquakes. The example, he's gone, okay, the San Andreas Fault. That's along the California coastline. It's not a converging plate, it's a transform boundary, where one plate's moving north and one moving slightly south. I mean, very slow movement, but they get hung up there. You think it's bad news for them to have frequent earthquakes? That sounds like not a good thing. But if they don't have frequent earthquakes, that means the pressure is allowed to build for a longer period of time, and then when you do have one, it's going to be a major earthquake. So actually it's better to have little and smaller, frequent little ones than one big one or spaced far apart. San Andreas Fault is one of those transform boundaries. But, did y'all get all that? No, I'm sorry. Now, what Hudson Hunter was saying about Yellowstone, that's really frightening. Because, I mean, frankly, why Yellowstone is the geological wonder it is because you have lots of vents where hot material from the interior are making their way up, and that's why Old Faithful erupts. But yeah, Old Faithful is not the only geyser out there. When you see Old Faithful, when we were out there the week between summer and fall terms, we were waiting. We got there about 30 to 40 minutes before Old Faithful was supposed to erupt, and they give you a 20-minute interval, so you don't know exactly when. And while we were waiting, another geyser really close to it erupted and gave us a show, free show. It isn't as regular as Old Faithful is. Old Faithful is almost on the hour, not quite, but they can estimate it within. It goes from anywhere from I think maybe 40 to 50 minutes apart to an hour and 10 minutes. So it's not right on an hour, but it's very. That's why they call it Old Faithful. It's the most regular. Then we drove down in the Norris Geyser Basin. There's just a whole thing we didn't even begin to walk through it because we had to walk so far to even get to it. But you could just see just geyser after geyser. Some of them just sitting out with a little steam. Some of them you saw the cone with nothing coming out all along there. It's a very fragile area. So if there is something rumbling underneath there, if it were to go, it'll be, hopefully it wouldn't wipe out some of the incredible beauty that's there. I mean, it's just amazing. Okay, I left this up here. San Andreas Fault. Left it there for you. Okay. It's a transform boundary. Okay, everybody?
I'm sorry.
Huh?
You said it's a what?
Transform boundary, where they move past each other. Okay? Right. Not diverging, not converging, but moving parallel to each other. Transform boundary. All right. Now, what's our present day understanding? Probably pretty weak. Okay? There are, and here somebody asked this question, and I want you to read this. On page 471 in the new edition, bye-bye California? Ain't gonna happen. The San Andreas Fault is a transform boundary. It's not going to fall off into the ocean. That's not what happens with a transform boundary. It doesn't happen with any of the boundaries, by the way. Even places where they separate, new material comes up. I mean, so nothing falls off, okay? Subduction zones happen, but that's way beneath the surface. So it's a little blurb, well worth a read. What's our present day understanding of that? The major remaining question, among many, I don't know if this is major, what in the world is making the plates move? Why don't they just sit there? What makes them move? Okay? There's some current working hypotheses. This is saying one, convective cells in the asthenosphere. Okay? Now, again, if you'll allow me, no, people are writing. Remember that one that showed the diverging plates? The asthenosphere is reaching really close to the surface there. In fact, that's what goes through the crust. It's portions of that asthenosphere. So it's doing that. Well, if you have that kind of motion in the asthenosphere, then you have movement of it's sort of like currents in there. And they call these convective cells, where hot materials move up, cooler materials move away. Moving up, moving away. Well, guess what? That motion is dragging the plates apart from each other. So this is one. You have these convective cells in the asthenosphere. The hot fluid materials rise at the diverging boundaries. As some of it escapes to form new crust, the remainder spreads beneath the lithosphere, cooling as it is, but dragging the overlying plates with it. That's an idea. We just don't have enough evidence to say that's really happening. Okay? So that's one of possibility. Okay? I think, here will be the illustration of that. Here we have the hot, molten rock coming up, and then some of it escapes and forms that ridge, and others moves down along here, dragging the plates further and further apart. Okay, so that's one possibility. Now, while we have that slide on here, I don't think we have another one coming up. Well, we might. I may hold off on that one. Okay? If we don't, I'll come back. But this shows that convective cell. Now, this is a really compressed shot. Here's the core down here, which is molten, very, very hot. And here's the part of the mantle, the heat coming from here and the magma coming from here goes up. Some escapes and others of it dragged down, and that's pulling them apart. Okay? That's one theory, one hypothesis, not even as much as a theory. Okay? Now, that was the last slide, so they don't show the next one. On the next page, another one is shown, but it's still on here too. The other is this, where subduction is already occurring. Now this is pulling this plate along because it's going downhill. And some of it's becoming molten material again, melting here. So therefore, it leaves a gap and it pulls out. So this is called one of them is called the drag and the other is called the pull. I think this is in your text. It was in the old version. Let me see if I can find it. The one that was described here is the ridge push that's pushing it down, and the other is called the slab pull, which is pulling it down. Okay? Now, it could be both. In fact, my guess is it's probably some of both. Who knows? It may be neither as well. It may be something else that's causing this that we don't even have a clue about. But those are the two major ideas now. And you can kind of see them both from here. If you do have this convective cell here, then this is the ridge pushing it further away, and at the same time, the drag here by the ones that are being subducted, that would be the something pull, slab pull. Slab pull. All right. As I said, people behind the science, Harry Hammond Hess. That's a very alliterative name, isn't it?
Say it 3 times fast.
Say again?
Say it 3 times fast.
I can't even get it once. Okay. All right. Now, he died in 1969, but he was around during World War II, and he did many, many, many of the great experiments and tests and research on mostly the Atlantic. He may have done some in the Pacific too, but and if you read through this, you'll see some other names. You'll see names of his ships, and you can find out all sorts of stuff in here. Well worth a read. And then, Science and Society, geothermal energy. We talked about that some with Iceland. They do some in the Pacific Northwest. I can't remember the name of the company up there. It starts with B, I believe, but I can't remember. It escapes me now. But there's several places that do have some pretty major geothermal power plants. Hawaii, California has 10 sites. Hawaii, Nevada, 10 sites. Oregon, Utah, 2 sites. So there's a bunch of places that do take advantage of that. So I'll let you read that. There's several questions. If you want to follow that up, that could be paper topic. Harry Hammond Hess, or some of the other people mentioned there, would be great paper topics. Okay? There's yet another slide on page, not slide, they should have had it in the slide but didn't, on page 474 showing the slab pull, and it gives you some illustration of that. Whereas the one on page 472 was the ridge push, and the one on 474 was slab pull. Combine them together to the one that we're looking at there. New earthquakes and volcanoes could happen anywhere, anytime. Not really anywhere. It could happen in lots of different places, but they can happen in places you wouldn't expect as well. Now, nothing, you hear this every chapter, nothing replaces reading the chapter. But once you've read it, the summary's here, and this to me is a very short summary for a pretty major chapter, so I wouldn't rely just on the summary. Key terms, a pretty short list there too, so again, read the chapter. But applying the concepts, a few more questions than normal. 52 questions here. Good to take a look at those, okay? Now, of course, this means the test on chapter 17 will be the last 30 minutes today. The test on chapter 18 that we just finished will be the last 30 minutes on Tuesday, okay? And so 52 multiple choice questions there. Was there a question?
Oh, no, I was saying we have a test every week.
Huh?
I was explaining to him that we have a test every week.
At least, okay, right. All right. Then questions for thought. There's 16 here. Hang on to these. We'll talk about these later. And also 4 for further analysis. So a total of 20 questions there. We will visit those again today, later today. Mark those. Then your parallel exercises. If you wanted to do some of those, you could too. Group A have the answers in the back if you have the big books. Group B do not have the answers in the back. And then on Tuesday, the first 2.5 hours will be in chapter 19. And then the last 2 hours we'll do the lab that goes along with 18. It really doesn't go that closely, but it will go. No, we're doing that lab today. The one that goes with 18. We're doing that now. In fact, we'll start that in just a few minutes. So what I have to do is run down and get them because she wasn't there this morning to have it copied. So I'm going to end the slideshow. And if you want to take a quick break, you may. I'm going to pause the recording. All right. Y'all got copies of the lab. I know you spent the last several minutes while I was setting up reading the lab, so you know, very familiar with what it's doing.
You know us.
Good. Okay. Let's see. And remind me, in just a few minutes, I got to call roll again. Okay. Density of igneous rock. Igneous rock is defined there. They mentioned 2 of them, granite and basalt, and what our materials are. Okay. Did you get a copy of the lab?
Yes.
You did. All right. What we have here is our balance over here. Right here, also it's called the scale. You take on move it sort of here because it'll be more simple. Okay. We have an overflow can. That will be my overflow can. Okay. And this will be our filling can. Okay. Probably needed to bring another, but I just didn't have enough cans. We'll manage. Okay. Ring, sand, and ring. We've got those here. We're not going to deal with the string. We got a beaker that's sitting right there. We got a granite specimen. All right, we have the equipment here. Now I have there it is. All right, here's our piece of granite. Now this is dark granite. This is a brownish kind of granite. So this may be a little denser than you would otherwise have expected, but it's the only one I have that would fit the scale and everything. And then we have some basalt, or at least it's what I'm thinking it is. It's dark color, fine crystal size. My guess that's basalt. Okay. We have 4 little pieces of this. The bigger you get your measurements, the better precision you get. So that's all I could find of it. All right. So what we're going to do first is someone wants to do the first weighing. Okay, who? Okay, come on. Okay, come on. Okay, the first thing you got to do is zero the scale. Okay, so you can turn that knob until you're on 0. Okay, and I think it said basalt first. So place these 4 on the scale. Okay, she's breaking my basalt. All right. Use the balance to find the mass of the basalt. And this scale, by the way, is measured in grams. Every little mark is a gram there. And give it your best guess.
63?
Say again?
Oh. What's that 63? What? It's 163.
163 is what she says. Okay? So on the back page of your lab, mass of basalt, 163 grams. Is what you said?
Yes.
Okay. I'm trying to say this loud enough so it gets recorded too. So 163 grams. Okay? Record the mass on the back. Okay? Now. Now what we're going to do is determine the volume of it. So what we're going to do, and I wish I had. Not that I thought you needed. Now, what I'm going to need to make sure this held down because when you put this water in, it tends to tilt. And this is like a video game. You aren't supposed to tilt it. Okay. Well, that wasn't a bad guess, was it? Pretty good. For a rookie, yeah. Now, if you'll fill that with water. Yes?
It's 3.5.
Okay, I need to call roll again. Oh, okay, let me go. Oh, okay, I told you it's time for a shower. Okay. You can stop it. You won't need that much. Okay. All right, you want to come on and pour? I'll hold this down. Or somebody can pour. Okay. Yeah. Now, I think I need everybody to come take a look at this. As he's pouring.
You gotta make a mess.
Need y'all to tell me when you think it's full.
Hold
There's some. Keep going. It's nowhere close yet. Okay. Stop somewhere there. Don't have the balance like that. Okay. That's a little bit better. Stop some more. Okay, everybody can see it? Okay, keep on going. I don't think you're there yet. Okay, y'all think it's full yet?
Yeah.
Okay, I don't think it'll hold anymore.
Yeah.
Let's try and see.
I think it will.
How about now?
See it rising up.
Okay, you think it'll hold anymore?
No, man.
Try and see. Oh, he did do it. Notice it is overfilled. Anyone know why that's true? You can pull that stuff out. Anyone know why that's true? Why it's actually above the top.
We all float down here.
Okay. What the reason is the surface tension of water. Surface tension is incredibly strong because of the hydrogen bonding, which we won't get into in this course. But that is a very, very strong force, and it's hanging on to those water molecules, not letting them fall. Okay, so if someone wants to get those 4 pieces, you 4 people get 1 piece each of that basalt. This is where the art comes in. Okay? Now, not very artful. Okay. Now, what you need to do is hold it as by one corner and let it lower in there very slowly. The water will start going into the overflow can. And right before your fingers touch the water, then let go and let it fall. Try not to have any splashing. You don't want any. Okay, here it goes. Here's going to be a demonstration of how to do it artfully. Probably need to start that over.
Yeah. So we get lit.
A little bit more. We've had some drill. Give you a little bit more. Okay. For a little more in there, for over the place. See, it does go over the top. All right, we'll try again. Try to make sure this is over here. Okay. Or corner. Okay. Let it go down very slowly. Very slowly. So long as it doesn't splash. Very slowly before it touches your finger. Like that. Okay. Next. Good. Next. Good. Next. All right. Now, I forgot to ask you, how are we going to determine the volume of this? Do we need to measure length, width, and height? Well, that was irregular surfaces. They weren't quite straight. How are we going to do volume? Huh? We already got the mass, so we need volume to get density, right? Well, we'll determine the volume of water. So what we're going to do is take an overflow can here, pour it into there. That's just because it has a wide lip and it's easier to pour than try to pour it there. So take that and pour it into that. So get all the drops, every drop down to the last drop. Good, like maximum hot coffee. Okay, now pour that into here. Slowly, hold still. So the volume of water there is the volume of what these pieces were here, right? Approximately. Someone read that? I think at least on a flat surface would be a little bit better. Okay, so get down to read. Okay, every one of those little lines is 2 cubic centimeters. No, I'm sorry, milliliters. So read that. What do you get? 51. Huh? 51. 51 milliliters, which is the same as cubic centimeters. So on your back of your page, the back page, the volume, 51, is that what you said? Cubic centimeters. Okay, someone with a calculator? Divide the mass by the volume, and what do you get? Okay, that's why I'm recording all this. Say again?
3.19.
3.19. Okay. What's the next digit?
3.20 really.
Okay. 3.19. It rounds to 3.19. Okay, 3.19 grams per cubic centimeter. Is that what you said?
But the next one, the 6 round to
3.20.
Yeah.
It goes up to 320.
Okay, so
3.20.
3.20 grams per cubic centimeter. That's the density. Now, I brought my book, but I can't get to it because I'm holding this down. If someone will find in the book, there is a table in the text. This is chapter 17. Okay? Near the top of what? 17, yeah, not the chapter we just did. Okay? All right. All right, what's at the top there? Huh? Oh, okay. Turn back. Back where you were. Okay. Slowly. Okay.
3.2.
Ah, what'd you say? In the book? Oh, you just read that. It's just a little table with the salt and granite. Salt in it. I mean, the salt. Yeah. Maybe I'm imagining it. I thought I saw it. Okay. Never mind. Okay, come on. Let's do the other. What's the next thing it says do? Take a piece of granite. So someone who hasn't done a measurement, re-zero the scale. Make sure you're zeroed. Yeah. Oh, you don't have a lap. Okay, right up here. I'm sorry, I can't leave because I'm holding this down. That's granite. Again? 445. 445? Okay. 445 grams of granite. Okay? Now, right now we had just what? Much less basalt, much more granite. Which you reckon is going to be denser? Okay, there's a lot more of it, wasn't it? Okay, someone wants to come and very slowly, carefully lower that into the water. Okay, come along. Whoever, if you didn't do one before. Did you do one before? Yeah. Oh, okay. We know you did something. You measured. Okay. There's the granite. The whole, just right corners, yeah. Okay. Go it slowly, slowly. Yeah, slowly. Don't make a big splash. Yeah. Before you touch your finger like that. All right. Now we need to dump this.
You want to take the basalt out?
What's that?
You take the basalt out?
No, why not? I mean, it was all in water and spilled over. It was all at the top. Okay, pour that into there. Got it all? Good. All right. Let's calculate. 75, 175. That's milliliters, but it's the same as cubic centimeters. If someone has a calculator, then divide the mass by the volume. .54. Okay. What was the other? 3.20. Yep. Which you reckon is denser? Okay. Oh, 2.54.
Yeah.
Uh-oh. Okay, what I think happened, I'm not sure. I wasn't sure. I think some of the water spilled with the granite. We may have to redo the granite. Let's make sure we got all the water in here. Now, someone come and make sure that doesn't make a difference. I'll think it would. Yeah. Huh? I'm sorry. Still the same. Okay. What I'm going to do, I'm going to see if when I release it. No, it doesn't. Okay. I can't release it. All right. If someone will bring me my book, it's underneath the paper there. Yeah, I'm sorry. Yeah. I almost thought for sure. You don't hold it? Okay, yeah. Just the back piece will be fine. Right there, yeah. It doesn't look too bad. Let me see if I can find that. So I thought I saw it and thought we need to pay attention to that.
That's right. Oh, how about we? You know what I'm talking about.
Okay, what were the measures we had?
Which one?
Call out the name and the measure.
Salt,
Yeah,
163 grams of mass,
okay.
51 centimeters volume,
Uh-huh.
and the density is 3.2.
3.2.
Yeah.
And the other?
445 grams of mass,
Right.
175 cubic volume,
Uh-huh.
and 2.54.
Okay, what were you telling me? Which is denser?
We thought it was granite.
Well, look at it. What's the density?
Does more mean less?
Huh?
Just more mean less. Which one is denser? Does more mean less?
Okay, look at the
Well,
density.
this means
I see what less is, what the number is, but does
Which
more
is
mean
greater
less?
density?
that means the salt is greater
The
than
basalt is the greater density. I thought so. Then when you said the second time, I thought you said 2.2. Oh, that's great. Okay, you did right. Y'all did good measurements. Okay? Now, what I'm going to do, I think.
You need help?
Here's what I'm going to do. Let it go now. Okay. Yeah, what are y'all doing telling me it was granite? Okay? It was basalt by a good amount. One film. Yeah. Okay. Okay. Now, guess what, team? That is all the questions. Okay, wait. That's six blanks there. Okay? Let's turn back to results on page 336. In what ways do igneous rocks have different properties? In what ways do igneous rocks have different properties? Give me a few. Density is one big one. We just determined it. Say again? Someone said something?
The iron in them? Isn't that
Okay, content, mineral content. Very good. Any others? Color?
All right.
Wait, color.
Color.
Yeah.
Different properties.
Okay.
Didn't do the last lab? Yeah, okay. Okay. There's other things like hardness and things like this. We didn't do any measure of that. Okay. So those are ways that they have different properties. Explain the theoretical process or processes responsible for producing the different properties of the igneous rocks. Okay. For instance, which one was the first one you said? Density. Now, what would be a theoretical process responsible for producing different densities in the igneous rock?
weighing them here?
The what?
Weighing them when we have them here.
Okay, yeah, but that's what we did to determine it. What produced that? Why did basalt was denser than the granite?
I don't understand, I guess.
Okay, why was the basalt denser than granite? What part of its
It's
process
mineral
for
content?
producing that? Say again? Okay. Now, when he said different layers in the earth, that could contribute some by different forms of compaction that went into it. But you see, granite is an intrusive igneous rock, which means it probably was somewhere inside the earth, whereas basalt is fine grained, it's extrusive. So it was under the ocean probably, but probably didn't have that big a difference there. Okay, let's think of some of the other properties.
Mineral content.
Mineral content.
All right.
Because what it's made up of.
Okay, and what was basalt made up of?
I don't remember.
Iron. The dark color gives that away. And what was the granite?
It's a lot of different.
It's a lot of different, yeah, it's a mixture of several, but because it's lighter color, it will have more quartz in it, maybe feldspar. This has more feldspar, but because it doesn't have as much iron, has more silica, iron is denser than silica. So therefore, the mineral content contributes to the density. Okay? So that's one. It also contributes to the color. The darker the color, generally the more the iron content. Okay? And then what you were saying about crystal size and depth, which those might have little effects, but I think these are the bigger ones. Does that make sense? Okay? Number 3. According to the experimental evidence of this investigation, propose an explanation for the observation that the bulk of the Earth's continents are granite, and the basalt is found mostly in the Earth's interior. Okay. Where does less dense stuff usually go?
The outer.
Yeah, it goes outer, and more dense stuff settles slower. So that would have the granites forming the continents that kind of float on the asthenosphere, and the basalts are deeper, denser materials go further down. Does that make sense? Yes.
Could you repeat that so I can write down the sheet?
Okay. What we found in this experiment, which was denser? The basalt. So therefore, as the basalt settled out, it would settle out lower, and the granite, since it was less dense, would tend to rise to the continental part. Okay? Now, number 4, you need to answer, but you answer it however you see fit. First, what's the purpose of the lab accomplished? And then give a little bit of a reason. A sentence we usually do. Okay? Now, what you've just filled out, 6 blanks you filled out in the back, 4 questions you answered on those 2 pages, that's 10 points worth. The lab is worth 25 points. Where are we going to get the next 15 points worth?
Questions at the end?
The questions at the end of the chapter. Very good suggestion. Okay. Okay. So if you turn to the back of the chapter, and remember this is chapter 18, the one we just did. Is it going to be the applying the concepts? No, those have the answers given. Okay? No, we wouldn't do anything simple like that, would we? We go to questions for thought. There's 16 of those, and there's 4 for further analysis. Okay? So that's a total of 20 questions you have there. You need to do at least 15 of them. Okay? I would say 15 or more. You want the lab or? Okay, so bring it in. Yeah. Okay, you got a copy of the lab. Okay, you'll need to listen to it on YouTube. Okay. Okay, yeah, when do you want to do that? I got it now. You want to do it now? Okay, wait just a second. Let's see. This is the previous chapter, right?
Yeah. The one about these.
Test 3. Test 3. There it is.
You want to bring the other one too?
You can stay in there. I was going to get it. Okay. Now, like I was saying, do 15 or more questions from questions for thought or for further analysis. You got 20 to pick from. Do at least 15. Now, why would I have said 15 or more?
Get more points.
Okay. You can only get up to 25 points, but you could lose points if you don't have right answers. So by doing more than 15, you have a better chance of getting the full 25 points.
You're right.
answering these questions, are we to do this online or something, or where, when, how?
You mean, where do you get the questions?
I know it's at the end of the chapter, but are we just, so we're just writing these
Yeah,
down?
write them out and turn them in with the lab. When you turn in the lab,
Do we
you
just
can write
write
them.
the answer now?
Yeah, put the, okay, if you
Question
want to
number?
not write the questions, I don't require you to write the questions, but do QFT for questions for thought or FFA for further analysis. Then put the number and put your answer. Okay, or if you want to write the question, you can do that too. Okay, so you got 16 and 4. Do any 15 or more of those 20 questions. Okay, make sense? Write the answer. Now you can keep it fairly short. A sentence or two will answer every one of these. You know, you don't need to write a paragraph or two.
Let me see them.
Okay, you can take a picture of them if you want to.
I just want to make sure we're on the
Easy
same
to
page.
do.
Chapter 18.
Chapter 18, questions for thought and for further analysis.
And when are they due?
Okay, here was the question. When are they due?
Never.
There was a dream. Wake up. Okay. Now. Okay. Here's the answer to that. Remember, your labs are due 1 week from the day you do them. So next Thursday is when they're due. However, okay, get this, people. However, since the test on Chapter 18 is next Tuesday, I would highly recommend you doing these questions and getting the answers before Tuesday, because this is a great way to study for Chapter 18 test. So I would say try to get them done this weekend. You don't have to turn them in until next Thursday, but if you get them done before Thursday, you can turn them in Tuesday. That'll be fine with me. But you can't wait and not do them till. So I've had people wait and do them after they took the test, and then when they turn in the question, they say, I wish I'd have done these before I took the test, you know. I'm telling you that. I tell them every time, and still people don't believe me, and they try not to. So, now, we have, let me mark the roll while I'm thinking of that. Hunter is still here. LaShondra didn't make it in today, did she? Okay. Rachel's still here. And Trey didn't make it in today, did he?
Okay, Ray did.
Okay, but Ray's still here. Jarrell's still here. Cece's still here. Let's see. Anthony didn't make it in today, did he? Okay. Sean's still here. Fred's still here, mostly. Okay. Chelsea's still here. Sam's still here. Nick's still here. Melva's still here. Willie's still here. Lisa's still here. Tiara didn't make it in, did she? Okay. Angel didn't make it in, did he? And Ashlyn didn't make it in, did she? But Kedrick is here. Okay. Now, here's the deal, folks. You have two options, maybe more. Okay? I'm here to help you if you get stumped on questions. It is lab. You can work together on the questions. This is a lab. You work together as a team. You can work pairs or groups or however you want to do that. Or the other option is you can go and take your test now and take the thing home and work on them without any assistance. Okay? So I'll let you decide. Now, since this is probably not the most comfortable places to sit on these stools, if you want to go back to the classroom, you can, and work on there and get your group test together and stuff like that. Or if you want to take your test, I'll be in there in a few minutes. I got to shut this stuff down here, and you can take your test whenever you want to. So it's all up to you. Any questions? Yeah.
I get last week's lab.
Okay.
I wasn't here.
think you can hear most of it on. Oh wait, yeah, that's the one we did in the
computer lab.
Computer lab. But I think you can hear most of what you need to know what to do on it. There's properties of common minerals.
We just did a lab. We didn't take a test.
No, the test for that chapter is. Oh wait, we did a test sometime on the Earth Moon system. Did you do that?
Pretty sure.
Okay, yeah. If you did that, yeah, that's the last test before today's test.
You know what the questions were on there?
You
just showed me. I can't remember.
I'm trying to recall. Questions of the sun. Test 4. No, that's the one we're doing today.
Yeah.
There it is. Let me see if I've got you. Let's see here. Test 3. This was the easiest way. Why don't I think of this? Miss Kelly. Yeah, I got you. You've already done it. Okay, thanks.
I'm going to take my question for that thing home when
Okay, you're going to do the questions at home. So I'll grade this part, but I won't complete the grade until I get those.
Okay.
Okay, so you're going to take the test now?
Yes.
Okay. Go to the classroom. I'll be there. I've got to move everything down there. Any other questions for Paul?
Turn it in or wait till we get our questions done.
It's up to you. If you want to keep them together, keep them together. Here's what I found. Sometimes when people turn the papers in, I turn that lab in, I don't have to do anything else. And at the end of the term, I said, are you ever going to turn this one in? They said, I turned that one in. I said, no, you turned in the first 10 points for us, but you don't have it. Oh, wow. So it's up to you. Whatever you can remember and go on and stuff like that. Yeah, I'll be in there in a couple minutes. Any more questions before I shut down and start recording? Stop the recording and start uploading. Okay. What's that? Okay.